Physics 2048, so physics for engineers. So if anyone's in the wrong place, everyone's supposed to be here for that, right? Okay, awesome. So this session is going to be recorded and posted online for people who can't be here. So I'm going to be going over the review that I posted online. If you guys haven't been able to get it yet, it's on the Study Union website. And also, if you guys have any questions, just let me know, and I can go over those too at the end. So is there anything like specific that you guys want to go over, like you have questions about? Yes? Okay, torque and moment of inertia. So I think there's a little bit of that in the review, and then at the end, if there's still anything like that, like we can go over like specific, into more detail. Okay. So everyone ready? Any other questions or anything? Okay, cool. So this is the review. Okay. So number 1, a student at the top of a building of height h throws one ball upward with a speed of vi, and then throws a second ball downward with the same initial speed. So the question's asking which final speed will be greater or if they'll be the same. So in this case, they would have to be the same because when you look at the formula, like vf squared equals v naught squared plus 2ad. The distance, the net distance in this case, is going to be 0. So that means that vf will be equal to v naught for the ball that you're throwing upwards. So in that case, then it's going to be the same magnitude because after you throw it upward and it comes back down, this is going to be vi and this is going to be vf, and they're going to be the same. Okay? And if you guys have any questions, like as I'm going through, if anything doesn't make sense, just let me know. Okay, so number 2, it's talking about a vector A, and it says that it has a negative x component. So the negative x component will be 3 units. And the x component is going to be I, and then we have a positive y that's going to be 2 units. So that's going to be plus, 2j. So that's going to be the answer for part A. B is asking the magnitude. So the magnitude you find by doing the square root of each of the components squared. So negative 3 squared plus 2 squared equals the square root of 9 plus 4, which is the square root of 13. Okay, so that's your answer for part B. C? Yes?
Is there any way to make the screen brighter?
Yeah, I can try. Sorry, hold on. Is that better or worse? A little more? Okay, yeah. Hold on. Is that okay? Yes. Okay. I can try to write a little bit darker. Okay. So it says when vector B is added to A, then the resultant that you're going to get has no x component, so there's 0 I, and a negative y component that's 4 units, so a negative 4j. So that means when you do B has to be, sorry if you guys can see that. Okay, negative 3i plus 2j. So I just plugged in for A over here, if you can see that. And then that's going to have to be equal to 0i minus 4j. So then when we divide it into components, we don't know what B's I component is, so we're going to say BI. And that's going to have to be minus 3i. For the component of A, that's going to be equal to 0. So that means that B I component is equal to 3. Then for the J components, you have like the B J component plus 2J equals negative 4J. So the B J component is going to be negative 6. Okay. And then when you put that together into vector form, you have, 3I minus 6j. Okay? Everyone can see that? Sorry if it's a little crammed at the bottom. Okay, so moving on to number 3. Yeah, you can't see it? Okay. Yeah, hold on. Is that better? Okay, yeah. Great. So 3. It wants to know the maximum, when you have the maximum distance, what your acceleration is. And if you guys recall the formula for that, which should provide you on the exam if they ask you a question like this, x max is equal to 2v naught squared sine angle cosine angle over acceleration. So when you're throwing something the maximum distance, the angle that you're going to want to use is going to be 45 degrees, because that's going to give you the maximum x distance. So since we know that our distance is 15 meters, our v naught is 3 meters per second. Then we have sine 45 times cosine 45 all over the acceleration. So when we move acceleration over to this side, and then we can divide 2 times 9 times root 2 over 2 times root 2 over 2 over 15. And, sorry. If you calculate that, then the answer you should get is A equals 0.6 meters per second squared. Okay. Sorry. Any questions on that? Confused? Okay. Does that make sense? Is there a part of that that's like wasn't clear?
Could you also solve with kinematics?
With kinematics? Yeah, you can. I believe so. I think I'm not sure if you have enough information to use an actual formula, because all you have is your initial speed. Yeah, like this is generally the best way to solve it. Like it would take a lot longer to solve it with kinematics, with other formulas. So this is the kinematic formula that they would provide you in this case. Okay? Yes? This formula? So that, they would give you that formula. Like it's usually on your formula sheet when you're taking a quiz or your exam. Have you seen it before? Oh, okay. So if your professor hasn't gone over it, I would assume that they wouldn't give you a question on it, because for us there's like another formula for maximum height. Yes.
I was going to ask, is there any way you can draw like a diagram of the formula?
A diagram. Kind of. It's not really. It's something that was derived in your textbook. Like you'll see it. They derived it from other formulas. So you could derive this yourself, but it would take a while. It's in chapter 4 if anyone wants to go look at it. Chapter 4 in the survey book, that is. So, okay. So number 4. A projectile is fired from the top of a cliff of height h above the ocean. The projectile is fired at an angle above the horizontal and with an initial speed vi. Find a symbolic expression in terms of the variables vi, g, and theta for the time at which the projectile reaches its maximum height. Okay, so the way we want to begin is first I can draw it's going off the cliff. It's fired at this angle. This is the height. And it has a speed vi. Okay, so it wants you to put it in terms of vi, g, and theta. So the first thing you're going to want to do is that your v, y, f is equal to your Vyi minus gt. In this case, like g is your acceleration. So you don't know your like time yet. So what you want to do is put it in terms of time. So if you know that your your Vi, like y initial, is going to be Vi sine theta minus gt, and then your final y velocity is going to be 0. So that means that when you rearrange this in terms of t, you get that t is equal to Vi sine theta over g. And then, so that would be, so this would be the term for time. Sorry? Oh, sorry. Yeah, there you go. Okay, so that's part A. Part B, we're going to use part A to find our maximum, our H max. And our H max is going to be taking into consideration this and also like whatever this height is. So we'll call that big H. So the big H is going to be equal to Vyit minus 1/2 gt squared. So when we plug in for, what we want to do is plug in this value for t. So then what we're going to have is Vi sine theta times Vi sine theta over g minus 1/2 g Vi sine theta over g squared. So when we solve for that, what's going to happen is these are going to be like Vi squared sine squared theta over g. And then when we solve for this, we're going to get this, one of the g's is going to cancel out with this g, so we'll have Vi squared sine squared over 2g. And then when we subtract for that, we'll get Vi squared sine squared theta over g. Okay, that is, so then for part C, okay, sorry, if everyone can see that, I don't know. Is that good for everyone? Sorry, I'm trying to write like neater. G squared theta. Okay. Oh, sorry. I totally like, so this is going to be like half of this. So this is going to be over 2g. Like this is going to be twice over 2g, and then this is going to be once. Is that better for everyone? Okay. Then for part C, I'm going to do that over here. We're trying to find the maximum height. So this is H max. So this is going to be in taking into consideration, like not only, sorry. Oh, is that the whole problem? Sorry, I'm getting a little bit like disoriented. Oh, okay. So our H max is going to be equal to, that height was the height that we found that is above the cliff. And then we want to add that to the small h. So that's going to be h plus like the big H that we found. So when we add that, it's just going to be equal to Vi squared sine squared theta over 2g plus h. Okay? So basically, this is like a problem you would have, except it's more abstract. I'll show you the concept. Okay, number 5. So a 1,000 kilogram car is pulling a 300 kilogram trailer. Together, the car and trailer move forward with an acceleration of 2.15 meters per second squared. Ignore any force of air drag on the car and all friction forces. So it's telling us that we don't have to worry about the friction force. And we just want to know the net force on the car, the net force on the trailer, the force exerted by the trailer on the car, and the resultant force. So starting with part A, what we're going to do is the force on the car is going to be equal to the mass times its acceleration. So we know that its mass is 1,000 kilograms and its acceleration is 2.15 meters per second squared, and that's going to be equal to 2.15 times 10 to the third newtons. Okay? And then for B, okay, that's part A. Part B is just on the trailer, so we're going to go through the same process. The mass is 300 kilograms this time, times 2.15 meters per second squared. That's going to be equal to 645 newtons. Okay. Then for the force exerted by the trailer on the car, so it's going to be the same as the force of the trailer, the net force on the trailer itself. So that's going to be 645 newtons as well. And that's because the way, I guess if you draw a diagram, this is your trailer and this is your car. So when you have a force of 645 newtons on the trailer, then that's going to be 645 newtons that it exerts on the car as well. Okay? Part D. So then for our resultant force, we have to take into consideration our force of gravity. Sorry. Which is going to be, on the car, is going to be 1,000. And then saying that gravity is about 10 meters per second squared. This is more of an estimate, like not 9.81. Then our force is going to be 1 times 10 to the fourth newtons. I'm going to zoom out a little bit. Can you guys see that still? Okay. And so our net force is going to be a combination of both the force of gravity and also our like 2.15 that we have that was already on the car. So then our net force is going to be the square root of 1 times 10 to the fourth squared plus 2.15 times 10 to the third, or sorry, 10 to the third squared. Okay, so that's going to be equal to 1.02 times 10 to the fourth newtons. Okay. So moving on to number 6. We have two objects connected by a string, and there's a pulley right here. If you can see that, that's frictionless. So our incline, our angle is 55 degrees. M1 is equal to 2 kilograms. M2 is equal to 6 kilograms. So we want a free body diagram first. The free body diagram for mass 1 is going to have mass and gravity going downwards and tension going up. For mass 2, we're going to have a normal force going up. This is going to be mg, mg times sine of the angle. Let me see that. And then we're going to have the tension going this way. And I believe, yeah, it says it's frictionless, so we don't have to worry about friction. In this case, what we're going to do for like the acceleration is for the first one, or for mass 2, we have mass 2 times g times sine of the angle. That's going, oh, sorry, okay. This was like poorly represented. So we also have a force of gravity in this direction, and that's what's going to be pulling the object down while the tension is pulling it up. So it's going to be accelerating like in this direction. So m2g sine angle minus the tension is going to be equal to the mass times the acceleration. The way that it's accelerating depends on which one is heavier. Since mass 2 is heavier, it's going to actually be going like this way. But either way, if you assumed it was going the other way, then you would just get negative numbers for your acceleration, which would show you which direction it's going. So when you have that, you can just plug in. So we have m2, which is 6, 9.81 for gravity, sine of 55, minus tension equals 6 times acceleration. And we don't know what tension is yet, so we can use our formula for mass 1 to find that. So the only forces on mass 1 are mg and tension. So mg, so in the y direction, it's going to be balanced out. So what you want to do is find that like t minus mg is going to be equal to m1a. So your t minus your 2 times 9.81 is going to be equal to 2 times the acceleration. And the acceleration for both of the objects will be the same. So using these two formulas, you can like plug them, like you can say that t is equal to 2 times a plus 2 times 9.81, and then plug in for t. So you have plug in for t in this formula, sorry. So you have 6 times 9.81 times sine 55 minus 2a minus 2 times 9.81 equals 6a. And then solving, you can like add 2a to both sides. And when you solve for a, you should get a is equal to 3.57 meters per second squared. Okay, and then using the same process, like we can use either formula to find tension since we already have the variable a. So in this case, we can say like tension minus 2 times 9.81 equals 2 times 3.57. And then our tension is going to be equal to 26.74 newtons. Okay? So that's our tension. This is our acceleration. Okay, number 7. So what we want to do first is we have two different objects moving in opposite directions. This one's going to have a force of friction right here, and this one's going to have a force of friction going the opposite way. So let me draw free body diagrams on both of those for you. So we have M1, which there's going to be a normal force, a force of gravity, which is M1g. And then we have our friction force is going to be going this way, because this one is sliding, so this one is sliding this way. So the friction force is going to cause it to go this way. And then we have a tension force, since it's attached to a string right there, going this way. Then for block 2, it's going to have not only a normal force going up, but also the normal force of the first one coming down on it, and a gravity force right here, as well as a friction force from itself sliding on the ground, as well as sliding against block 1. And then it's going to have the force that's pushing against it this way, which is 45 newtons. Okay, so looking at block 1, the only forces in the x direction we have are the friction force and the tension. So that means that tension is going to be equal to the friction force. And we can find the tension because we know like or we can find the tension by finding the friction force. So we know that the friction force is going to have U m1g. This is the normal force, mass times gravity, and then our like friction, which they give to us. Yeah, the coefficient of friction is 0.2. So we have 0.2 times, sorry, the upper one is 5 times 9.81, and that's going to be equal to 9.80 newtons. Okay, then looking at block 2, if we look in the x direction, we have the force going this way. Going to the right, they say it's a 45 Newton force minus the first force of friction and also the second force of friction. And then it's going to be accelerating. That's going to be equal to the acceleration in the x direction times its mass. So this is just like a review. So like when we're talking about like acceleration in the x direction, if it was staying still, then it would be 0. And that's why we did 0 for the top block, because it wasn't moving, but this one is accelerating. So it's going to be equal to the mass times acceleration. So our friction 2 force is going to be equal to the coefficient of friction, and then it's going to include both masses. Since mass 1 is sitting on top of mass 2, then they're both going to have to be included like in the friction force. And then that's going to be times gravity. So when you calculate that out, you have 0.2 times 15 times 9.81. You should get 29.4 newtons. Okay, and then when we plug all this back into the formula, so we have F equals 45. F equals, 45 newtons. That's the horizontal force they give us. Then we know we already solved for F1, which is 9.8 newtons. And we just solved for F2, which is 29.4. So we know that 45 minus 9.8 minus 29.4 is going to be equal to mass 2, which is going to be 10 times the acceleration. So when we solve for this, what we're going to get is that the acceleration is equal to 0.580 meters per second squared. Okay, so like what this was doing, here, I'll write this more clearly, was the sum of forces in the x direction, and this was doing that as well. Okay, so number 8. A pail of water is rotated in a vertical circle of radius 1 meter, and then there's going to be 2 external forces acting on the water pail. So remember that when you're like any object that is going to have a gravity force on it, but also when you're swinging it in a circle, it's going to have a centripetal force. And this centripetal force, in this case, is going to have to be greater than the force of gravity in order to keep the water inside of the pail. So we're going to write that the centripetal force has to be greater than the force of gravity. Our centripetal force, since force is mass times acceleration, we're going to have our mass times, and if you remember, our centripetal acceleration is v squared over r. And then that's going to have to be greater than or equal to our mass times gravity. So in this case, what we can do is cancel out masses, and we know that v squared over r is going to be greater than or equal to the force of gravity. So we know our radius, which they give to us, is 1. So v squared over 1 has to be greater than or equal to 9.81. So v squared is going to be greater than or equal to 9.81. And when you take the square root of that, then it should be greater than or equal to 3.13 meters per second. So, okay, that's going to be the minimum speed. Yeah, and then it's basically, it's like a projectile. So it would, for part C, when it's asking if it were to suddenly disappear at the top of the circle, would it differ from the motion of a projectile? No, it wouldn't, because it's acting as a projectile. We're just considering it as a point with just like one velocity. We're not considering it as a mass. Okay, so moving on. looking at number 9, we have a 100-kilogram bullet fired from a rifle, and so it has a barrel that's 0.6 meters long. So it's going to begin moving at the origin, and then it's going to be moving 0.6 meters. The bullet is 100 grams. And the force that's exerted is going to be 15,000 plus 10,000 x minus 25,000 x squared. And x is in meters. Okay, so it wants to know the work done. So if you remember the formula for work, work is equal to the integral of xi to xf of the force. So they gave us the force, and we have the distance as well. So really all we have to do here is, it starts at 0 because it says the origin. Our work is going to be equal to 0 to 0.6, 15,000 plus 10,000 minus 25,000 x squared dx. Okay, so when you solve for that, you should get that. You can just plug that into a calculator or solve it if you want to. But when you solve for that, remember that work is in joules, so you're going to get 9 kilojoules. Okay? And then, yeah, so that's it for that question. Number 10, a single conservative force acts on a 5-kilogram particle within a system due to its interaction with the rest of the system. So this f of x is going to describe the force, and it's in newtons. X is in meters. So the particle is moving from 1 to 5. What we want to do is calculate the work done again, and then also the change in potential energy and the change in kinetic energy. Okay, so we have m equals 5 kilograms. F of x, or the force, equals 2x plus 4. And then, so our work formula, remember, it's our work equals our distance, which our distance is 1 to 5, 2x plus 4 dx. So when we integrate that, we have x squared plus 4x from 5 to 1. And then, so that's going to be, when you plug all of this in, it's 25 plus 20 minus 1 minus 4. And that's 45 minus 5, which is equal to 40 joules. Okay? So that's your answer for part A. Our change in potential energy is going to be equal to the work is going to be equal to like negative the work amount of work done. So that's going to be negative 40 joules, which is what happens because the potential energy is converted to work. So that's why it's going to be the opposite. Okay, then our kinetic energy, if you remember the formula, our change in energy is going to be equal to our, I guess like our kinetic energy is going to be, hold on, sorry, KF. Okay, so we're given our velocity. So the kinetic energy starts with a speed of, if its speed is, okay, so it starts with a speed. So we only know our original kinetic energy, we don't know our final kinetic energy. This is our final kinetic energy, and our original is going to be mv squared over 2. So we know that mv squared over 2 is going to be equal to 5 kilograms times 3 squared over 2. Okay, and then our potential energy is converted to kinetic, right? So we know that our 40 joules is going to be equal to kinetic final minus 5 times 9 over 2. So when you solve for that, you should get that the final kinetic, is going to be equal to, here, I'll solve that out for you. So 40 plus 45 over 2 is equal to our final kinetic. And that's going to be 62.5 joules. Okay. So Moving on. So we're in about chapter 8 now. And looking at a 5, okay, so if this is a block, if you can see that, I don't know. It's going up an inclined plane. VI is equals to 8 meters per second. And it travels a distance of 3 meters at an angle of 30 degrees. So we're looking first for the block's kinetic energy and then its potential energy. So first, in order to find its potential kinetic energy, we're doing 1/2 mvf squared minus 1/2 mvi squared. So it comes to rest after it reaches this distance. So that means our vf is going to be equal to 0. So this entire part is going to be equal to 0. And then that means that we have negative 1/2. Our mass is 5 kilograms times 8 squared, which is going to be equal to negative 160 joules. When you're talking about energy, it's always going to be in joules. This is in kilograms, and this is in meters per second squared. So joules, is kilograms times meters squared per second squared. Okay. For part B, we're looking at the change in potential energy, which is going to be, it's usually mgh. In this case, we don't know what our h is. We only know our angle and our distance. So we know that it's going to be m times g times our distance sine 30. Okay, because, I'll just write this out really quick. So sine of our angle is opposite over hypotenuse. We know our hypotenuse length, which is d. So d sine angle equals this height. Okay. So when you plug in for that, you have 5 times 9.81 times 3 times sine 30, which is equal to 73.5 joules. Okay. So for part C, we're looking for the friction force, which it doesn't give us the coefficient of friction. So what we're going to have to do is find that, our change in, the difference between our kinetic and potential energy is what is going to be lost to friction. So since we know our delta kinetic energy and our delta U, what we have to do is find the difference between them, and we know that's going to be equal to our force of friction times distance, because our energy is equal to force over distance, and this is the friction force. So we have negative 160 plus 73.5, and that's going to be equal to negative force of friction times 3. So when we have that, our friction force is going to be equal to 73.5 minus 160 over 3. And then when you solve for that, then you find that your friction is 28.83 newtons. Okay? And from this, we can find the coefficient of friction, because friction is equal to the coefficient of friction times the normal force. Our normal force is always going to be balancing out gravity. So in this case, with this block, we have mass times gravity going down, but then our normal force is going to be going this way. So that means that this component is going to just be mg times cosine theta. So our normal force is going to be equal to mg cosine theta. Therefore, the force of friction is U, or coefficient of friction times mg cosine theta. And knowing that that is 28.83, which we already found, we can plug in for the mass, plug in for gravity, and our angle is 30 degrees. So our coefficient of friction is going to be equal to 0.679. Okay? Does anyone have any questions at this point? Or was I going too fast through any parts that you want me to go back to? Okay, cool. Okay, continuing with number 12. So this is still chapter 8. Jonathan is riding a bicycle and encounters a hill of height 7.3 meters. At the base of the hill, he is traveling at 6 meters per second. When he reaches the top of the hill, he is traveling at 1 meters per second. So already we know that this is going to be our VI, and this is going to, this is going to be our VF. Jonathan and his bicycle together have a mass of 85 kilograms. Ignore friction in the bicycle and between the bicycle tires and the road. So we want to know the external work done on the system between the time he starts and the time he stops. And, okay, so yeah, let's start with that. So what you need to do to find like work done is you want, okay, the work done is going to be equal to the force times the distance, right? And when it says that it's done by the external work done, that means it's going to want a negative value. So in this case, the force, the only acceleration that we're taking into consideration here is gravity. So we have negative mg, that's going to be our force. And then our distance, our distance is going to be our height, which it does give us. So that times 7.3. Because potential energy takes into account how far it's moving. So this is the y direction, our gravity is in the y direction, and our height's in the y direction. And when you solve for that, you should have negative, our mass is 85, times 9.81, times 7.3. And that's negative 6,080 joules. Or no, sorry, I think that decimal is off. 85 times, let me calculate that really quick.
That's 6,080?
Yeah, or 6,087, but approximately 6,080 if you're doing significant figures. So, yeah. So that was part A. Part B is looking for the change in potential energy. Oh, sorry, the change in potential energy stored in his bike. So you know that the difference between the kinetic energy and the potential energy is going to be the work. And our kinetic energy we can solve for because we have his different speeds. So our original speed, our final speed is 1 meters per second. So we want to do our like kf minus ki. So that's going to be equal to 1/2 times his mass times vf squared, which we have, okay, so minus 1/2 mv naught squared. When we solve for that, we have 1/2 times 85 times 1 squared minus 1/2 times 85 times 6 squared. Okay, sorry, that's a little bit, let me rewrite that really quick for you guys. Okay. Equals 1/2 times 85 times 1 squared minus 1/2 85 6 squared. Okay. So you're going to get a negative number from this because the speed was greater initially, which shows that there was a decrease in kinetic energy, and you're going to get 1490. So plugging that back into the formula we have up here, we have negative 1490 plus delta U is equal to negative 6,080 approximately, which will show us that delta U, which is our change in potential energy, will be negative 4590. Okay. And then part C. Okay, the work done is just going to be like how much on. Our work done is like the same as our change in potential energy. So in that case, 4,590 joules like will be done in the positive direction, because that's how much potential energy was changed. Okay, so C will be 4,590 joules. Okay, any questions on that? Could you see all of it? Okay, great. Let me check the time. So, moving on to chapter 9, what we want to, okay, so here what we're looking at is we have a block and we're shooting it with a bullet. So we have the initial velocity of the bullet, but what we need to find, and we have how far it can rise off of the, here, sorry, I'll read the problem really quick. So a 1.25 kilogram wooden block rests on a table over a large hole, as in the figure shown. A 5 kilogram bullet with an initial velocity is fired upward into the bottom of the block and remains in the block after the collision. The block and bullet rise to a maximum height of 22 centimeters. So first you want to describe, okay, they tell you to describe because what you're looking at here is not just like a conservation of momentum problem, but a conservation of energy and conservation of momentum problem. So the first thing that you need to look at is the change in energy. So your change in potential energy is going to have to be equal to your change in kinetic energy. In this case, we have it's only moving in the y direction, so mgy is equal to 1/2 mv squared. Okay, so you can cancel out m on both sides. This is for the bullet. Because the bullet starts with a velocity, we don't know what its final velocity is going to be. So, like, sorry. So what's changing is that it is moving. Does it give you an initial? Oh, sorry, you don't know what its velocity is. My bad. Okay, so you only know that the mass, which is you know gravity, which is 9.81, and that it's moving rest on one table over large hole. Oh, sorry. Okay, so what you need to find out is, my bad, okay. I just started this problem wrong, okay. So the block, you know its mass, and you know the mass of the bullet. What you and you know its maximum height. So you're finding that like it rises 22 centimeters, which is the same as 0.22 meters. And you know that gravity is 9.81. So you can find what the velocity would have to be to make it rise that height, because it starts at 0. So our combined mass is going to be 1.25 kilograms plus 0.05 kilograms times 0.22 meters. Okay, times gravity. And that's equal to 1/2 the combined mass, m1 plus m2 v squared. Okay, so you can just cancel out the masses here, and you know that 0.22 times 9.81 is going to be equal to v squared over 2. So our combined final velocity in this case would be 0.22 minus 9.81 times 2. Or, yeah, sorry. And then you have the square root of that, which is 4.38 meters per second. So that's going to be the velocity after the bullet hits the block. But we still don't know the initial velocity of the bullet, which is what we're trying to find. And the only way you can do that is by using conservation of momentum. So you know that the bullet was moving at first. So the mass of the bullet times the initial velocity of the bullet. is going to be equal to the mass of the bullet plus the mass of, let's call it the mass of like mass 2, times this velocity right here. Okay, so the mass of the bullet is 0.005 kilograms times VI, and then the combined mass of the bullet and the block is going to be 1.25 plus the 5 kilograms. And then that is going to be multiplied by this velocity, because your momentum is conserved. So basically, in the original case, the only thing that was moving was the bullet, and it has this initial velocity. But in the end, they're both moving at this velocity, and this is their combined mass. So when you solve for VI, what you're going to get is that it was moving at 1,099.38 meters per second, which is fast, but that's how fast a bullet would move. So, okay, did any of that not make sense to anyone? Can you see it still? Okay, cool. All right, so we're almost at chapter 10. Do you guys want to take like a 10-minute break right now? No? You just want to keep going? Okay. I'm supposed to give, yeah, we'll just wait like 20 minutes and then have a break. Okay, so a rotating wheel requires 3 seconds to rotate, 37 revolutions. Its angular speed at the end of 3 seconds is 98 radians per second. So we want to know the constant angular acceleration, which it's telling us that it's accelerating and it's accelerating constantly. So that means that our angular velocity is going to be changing, right? So the first thing we want to do is convert our revolutions to radians per second. So we have 37 revolutions, and there's 2 pi radians in each revolution. Per revolution. So that's going to be 37 times 2 times 37. It's going to be 232.47 radians, which doesn't give us the speed yet. We can find that speed by dividing that by, oh no, sorry, that's our total like distance. So what we can do when we have like angular velocity, angular acceleration, and like distance in radians, you can use the same kinematic formulas that you would use for regular velocity, regular distance, regular acceleration. So in this case, what we want to say that the final angular velocity is going to be equal to the initial angular velocity plus our angular acceleration times time. Okay, so we know that our final angular velocity is going to be 98 radians per second. And, sorry. Okay, this pencil is not, okay. And then we know that it's moving for 3 seconds. And then in the same way that we're using this formula, we want to use the distance formula. So we know that our distance is equal to our initial angular velocity times time plus 1/2 our angular acceleration times time squared. And we just found our distance, which is 232.47. And then we can plug in 3 seconds for t, 1/2 angular velocity times, again, 3 squared. 3 squared. Okay, so what I would do in this case is subtract the angular velocity times 3 from both sides. So you have initial equals 98 minus angular velocity or angular acceleration times 3. And then you can just plug it in over here. Okay, so you have 232.47 is equal to 3 times 98 minus 3 angular velocity plus 1/2 alpha times 9. And when you are going to calculate that out, so you have 232.47 equals 3 times 98. These are all really big numbers, but I will try to fit them. Minus 9 alpha plus 9/2 alpha. Okay, so subtracting this value from both sides, you have 232.47 minus that. And then negative 15643.53 equals negative 9/2 alpha. And then when you solve for alpha in that case, what you should get is that alpha is equal to 13.67 radians per second squared. Okay. Also, if you guys don't catch me writing everything down, or you can't see it, then I'll leave this up here at the end so you can.
Where did you get the 15,876 from?
That was from just 3 times 98 right here.
3 times 98 is 15,876.
No, it is not. You're right. What did I even do? Yeah, it's 294. My bad. Okay. In that case, okay, the answer should still be correct, but I just wrote it down wrong. 94. Okay, so 232.47 minus 294.47 minus 294 equals, that'll give you negative 61.53 on this side. What? Okay, equals. Does that look better? Okay, sorry. All right, so moving on, number 15. Okay, this is a moment of inertia problem. It's saying a student is freely rotating on a stool and he's holding 2 dumbbells, each of 3 kilograms mass, and then he extends his arms so that they are 1 meter from the axis of rotation, and then he rotates with an angular speed of 0.75 radians per second. So the moment of inertia of the student plus the stool is 3 kilograms times meters squared, and this is a constant, so it's not changing. And then he pulls the dumbbells inward to be 0.3 meters from the axis of, the axis of rotation. So we're finding his change in angular speed. So what we want to do is say that, his total inertia, because the inertia of himself and the stool is 3, but we also have to take into consideration the dumbbells. So our inertia is going to be I equals 3. That's for this moment of inertia, plus 2 times 3, because we have 2 masses of 3 kilograms each, times our radius squared. Oh my gosh. Okay, times our radius squared. And our radius in the first case is going to be 1 meter. Okay, so that gives us, oh my goodness, a moment of inertia of 9 kilograms times meters squared. Okay. Then remember that due to conservation of momentum in our rotation, we're going to have the inertia times the angular velocity times our final. Okay, so this is going to be our initial, and then we have we have to find our final as well. Okay, so what we're going to do is, this was my bad. We're going to keep the 3 the same. The only thing that's changing here is the radius. So our radius is going to change to 0.3. And that's going to be 3 plus 6 times 0.3, which is, 1, 2, 2 times, oh, 0.3 squared. It's going to be 0.54. And then our moment of inertia is going to be 3.54 kilograms times meters squared. Okay? So we can find our original angular velocity, or it gives it to us, which is 0.75 radians per second. Okay, the student rotates with an angular speed of 0.75 radians per second. So what you need to do is find the final angular velocity. You can just plug everything back into the formula we wrote up here. So we have 9 times 0.75 equals the final, which is 3.54, times our final angular velocity. Sorry, where?
Is that an 8 or a 9?
This is a 9. So 9 times 0.75 divided by 3.54, our final is going to be 1.91 radians per second. Okay. Is that good for everyone? Yeah, makes sense? Questions on like inertia? All right. 16. Okay, so all we're doing here is locating our center of gravity, which is like kind of near the end. So hopefully like you guys just went over it, but either way, so we have like our formula is going to be our like center of gravity for x is equal to our delta mx over delta m. And the same thing for y. So this is just telling us that our, like all of our distances combined times our like mass over our mass, that's going to give us like where our center is. So the first thing that we have to do is divide this into different segments, because like the only way, like we need to look at them as separate rectangles so we can find the center of each. Okay, so in this case we're going to have one rectangle that's 18 by 4 centimeters and one that's 4 by 8. Okay. Sorry, does that make sense? Yeah. Okay. So what we want to do is find like the center of each of them. So for rectangle 1, so this is 1, this is 2. Our coordinates are going to be, our like x coordinate is going to be like the middle of 4, so it would be 2 centimeters. And the center of this one would be 9. Okay? And then for rectangle 2, the center of this rectangle for x is going to be in the middle of here, so it would be right here at 8, because this part is 8 centimeters long, and we have to subtract like this 4 because it's not part of the rectangle, so it's going to be 8, and then our height is going to be 2. Okay, so after that, what we want to do is find the area of each. So the area of rectangle 1 is 4 times 18, which is going to be 72 centimeters squared. And the area of rectangle 2 is going to be 4 times 8, which is 32 centimeters squared. Okay? And the reason we're doing that is because the amount of area in that section is going to be equivalent to like the amount of mass. So if like a certain like percentage of the area is located like in this rectangle, then that's the amount of mass we're going to have. So when we look at this like in terms of the formula, what we want to do is our like x value is going to be, well, I guess we don't need the delta. So it's this formula that we're using. For rectangle 1, we're going to use the area, which is 72, times the x coordinate, which is 2, plus 32, which is the area of the second rectangle, times the x-coordinate, which is 8. And then all of that over their areas like added together, so 72 plus 32. Okay, so that is going to be equal to 72 times 2 plus 32 times 8 divided by 72 plus 32, 3.85 centimeters. Okay, so our center of mass for our x-coordinate is 3.85 centimeters. And doing the same thing for the y, you have 72 times 9 plus 32 times 2 over 72 plus 32. And that's going to be equal to 6.85. Okay? Sorry if this wasn't clear. This is a y. All right, so everyone good on that one? Okay, last problem. So, find the mass of the counterweight needed to balance a truck with mass 1,500 kilograms on an incline of 45 degrees. So both pulleys are frictionless and massless. So the first thing that we want to do is draw a free body diagram. Okay. So with that, we're going to have our normal force, and our normal force in this case is going to be counteracted by gravity, so our mass times g, and then remember that since we have an angle here, it's going to be cosine of the angle. Okay? Because, okay, like this angle is going to be the same here. So, yeah, so it's going to be cosine of like the gravity. And then, because the gravity is acting like down, if that's not clear. Okay, and then we have like 2 ropes attached to it, so there's going to be 2 tension forces going this way that are going to be the same. And going downwards is mg sine angle. Okay, so first we want to look at our forces in this direction. So forces in, we're going to call that x prime. This is like, we'll say this is the x prime axis. And so the 2 tension forces are going to be, since it's telling us that it's balanced, so they're going to be equal to mg sine theta. Okay? And we don't know our tension. We do know our mass, our gravity, and our angle. So from that we can solve our tension, which our tension is going to be T equals 1,500 times 9.8 times sine angle over 2. And when I calculate that, times sine 45. The tension force is going to be equal to, okay, our tension force is going to be 5197 newtons. Okay, so that is, oh, so we're trying to find our mass. My bad. So what we need to do also is consider like this, and the easiest way to do that is to look at torque, okay? So our torque is going to be equal to 0. Since it's counterbalancing it, there's not going to be any movement, but we do know that we have an R and we have a 3R. So our force of mg, so our mass times gravity is going to be 3R away from the center right here. So our torque is going to be equal to 3, which is the radius, times mass, which is the mass we're solving for, times gravity, and that has to be counterbalanced by the tension times the radius. Okay? Does that make sense? So, So what we're doing is like we're going to plug in for gravity. So we have 3 times 9.8. Or 3r, sorry. 3r. So then our r's will cancel out. We don't know the radius, but we can cancel them out. Times mass equals tension times radius. So when you cross those out and you divide tension by 9.8 and 3, then our mass is going to have to be equal to 176.77 kilograms. Okay? Any questions on that one? Yeah, sorry. Uh-huh. Okay, so do you guys are there any, so someone said they wanted to go over a moment, I think she left, but do you guys want to go over a moment, or is there anything else that you feel like you're not comfortable with for your exam? Sorry? Oscillation? Harmonic motion, like circular motion? Chapter 15? Okay. I think, who do you guys have as your professor? New Pain. Do you all have New Pain? Okay, then never mind. It's like a variety, I guess. So, okay, is there a question you want to go over? Or, okay. Okay, so oscillation, spring, yeah, that's what I'm not. Yeah. Okay, we can go, yeah, we can go over that. So springs, I guess, the most that you would what you really need to know about springs is that the kind of energy that they produce. So if you're looking at an energy balance and you want to do conservation of energy, the energy of a spring, so I guess you could say I don't know how you guys denote it, but usually I do VE. So elastic energy is 1/2 kx squared. So that's something that you always want to take into account when you're doing an energy balance. So if you start out with a kinetic energy and then you're converting it to an elastic potential energy, if they give you a velocity, then and then it says how much, if you have a block and it has a spring, and then you have a ball that's hitting it with this velocity, then your kinetic energy of this m1, sorry? Oh yeah, sorry. Okay, so your kinetic energy is going to be 1/2 m1 vi squared, and then you can find the distance if they give you the constant k. So you have 1/2 k, and then if you can solve for x squared, or that kind of thing. There's different ways they might phrase it. Is there anything else in that chapter that is pendulums? Okay. I do not have one, but if you give me one, we can work it out. These questions? The original questions are online. Do you want the solutions?
No, I have most of the solutions. I'm just talking about where you put up the questions.
Yeah, if you go on the, it's UCF Study Union, a WordPress website, and you go to physics and under my review session, it'll be there. Or if you want to take a picture of it now, that's fine too.
Is it this website? Because I don't see it.
Sorry, can I see it? Thanks. This is the SARC website. Okay, I know it's really hard to find. Like, I had a lot of trouble finding it.
So it's a WordPress website?
It's also a WordPress website, yeah. Sorry, let me see if I can find it and I'll get you the link.
Is that where like all the different class?
Yeah, they have, and it tells you like the times that they're all at and all that kind of thing. So UCF, I think it's Study Union, WordPress.
This one?
That is not, that's the SARC website, which is close, but not quite. Oh my. Oh, it's a Google site. Sorry? And look up like a question. Oh, yes. The live stream, I believe, well, it's also going to be on that website. Sorry, let me try to find it really quick. It's here somewhere, I promise. Okay, I found it. It's ucfstudyunion.wordpress.com. Yeah, so that should be, everything for Study Union should be on that website. Okay, so do you want to, is there any other like major things that people are confused about? Just so we can like keep it in order. Okay, yeah. I haven't, people coming to my review sessions haven't really been talking about that, so I didn't know if your professors were covering it.
My professor was kind of like, oh, we did it until like chapter 12.
Yeah.
Thing said until chapter 15, but he said like it was a burn.
Yeah, yeah, that happened with a few of them, so I wasn't sure. You went to 15 still? Okay. Yeah, this review only goes up to 12 because a lot of people didn't know past that.
This one that you use?
Yeah, that's that one. No problem. Yeah, sure. Go around a radius R. Okay, let me write that down for you. Okay, so the question is, a merry-go-round of radius r equals 2.2 meters, has a moment of inertia of 240 kilograms times meters squared, and is rotating at, so angular acceleration I is going to be 9 revolutions per minute. Okay, then we're adding the weight of a 22 kilogram child, and who sits on the edge. So then we're trying to find the second angular velocity. Okay, so this is kind of similar to the one that we were talking about with like the dumbbells. You're going to want to also use, in order to find the original moment of inertia, you can use the moment of inertia of the whole thing, like without any, like without the child on it. So that's going to be 240 kilograms times meters squared. Sorry?
The mass for the child is 22?
Yeah, the mass of the child. Sorry, I'll write that like better since you guys don't have the question. Okay, of the child. So our original moment of inertia is 240, and our original angular velocity is 9 revolutions per minute. And if they want the answer in revolutions per minute, you can keep it in revolutions per minute, but usually like what they would want you to do is change it to radians per second. So if you wanted to change it to radians per second, what you would do is 2 pi radians over 1 revolution, and then that times 1 minute over 60 seconds. Okay? So when calculating for that, we have 9 times 2 times pi divided by 60 equals 0.94 radians per second. Okay. Then after that, we can use the conservation of momentum formula. So we have conservation of angular momentum, I guess I should say. So initial moment of inertia times initial angular velocity times our final. And we have this value, which is 240 times Wi. Oh, dang it. Okay. So our final moment of inertia, we can find by using the formula. I think you guys probably have it. It's like like the moment of inertia we have, which is 240, plus the mass times r squared. And the mass that we're adding is the mass of the child. And we're using the radius because it says the child sat on the outside of the merry-go-round, so that the radius is the radius they give us. So where's the mass? Oh yeah, 22 times 2.2 squared.
It's just MR squared, not 1/2.
Yeah, did I write 1/2?
No, we use 1/2 MR squared.
Yeah, for other things, I know. It gets confusing. Okay, so 240 times 22 times 2.2 squared. I did something wrong. Did I? What? Why does my calculator? Oh, plus. Okay, 240 plus 22 times 2.2 squared equals 346.48. So that's going to be our final moment of inertia. And we can plug that back into the formula too. So 240 times 0.94 equals 346.48 times our final angular velocity. So calculating by multiplying 240 times 0.94 divided by 346.48, our final angular velocity will be 0.65 radians per second. Okay. I'll try to find a problem on harmonic motion, if that would help you guys. Oh, okay. Thank you. Okay, cool.
And then it's just,
Right, okay.
we usually do questions every
I might need another piece of paper. Let me grab another piece of paper really quick. Okay, I'm just going to write on the back of this. All right. So the problem is, do you have the formulas by any chance either? Because I do not have them memorized. But okay, so the first question we're looking at is the block is 200 kilograms, or 200 grams, my bad. And the force constant is K equals 5 Newton meters. It's free to oscillate on a horizontal surface. It's displaced 5 centimeters from equilibrium. Our dis is 5 centimeters. And our V1 is 0. Or I guess our angular velocity 1 is 0. All right.
I feel like it's these ones right here. Where x equals
Okay.
xm cosine of wt plus phi.
The problem is we don't have an angle. Do you have the one for the, okay, the period is 1 over frequency. Sorry. I just don't, it's really weird.
This is before
Who's your professor?
Saha.
Okay. Yeah, I think you guys are probably the only ones who push through this far, which is fine, but.
My professor gave me the formula sheet, and there's nothing on harmonic motion.
Yeah, I know when I did it, we did do some harmonic motion, but.
We did fluids too, but he didn't teach you in class. He only gave us, you ever have homework on fluids?
quiz, and then teach it in class, and then give us a quiz.
That's terrible. I'm sorry.
I honestly hope
Well, no,
we
I
don't
mean,
go that far in the final because
No,
I'm pretty
you
sure most of the
won't
classes
because
didn't
it's
even
gonna
go
be like all the teachers give their in the final.
there. My
Yeah.
student got to 12 and he was like, okay, this is where we're stopping. We having a day for review. That's it.
Read gravitation and
well, it'll be good for you in the future.
Do you know if New Pain is doing
actually learning.
No, what I heard from New Pain is that he stopped at 12.
Yeah.
Okay.
Okay, then we don't have to do this since like half of us don't actually have the list.
I'm just trying to remember the formulas. It's
It's alright.
most of them, if you're able to figure out what the variables, like what each variable means, then you
Yeah.
can plug it in.
Yeah. I can bring out more questions from like chapter 12, 11, 10, etc. Because he has recitations for all of them. How viable they will be, I don't know. But
Yeah.
if you guys want,
Do you guys have any preferences?
anybody?
I just have a question. For
Yeah.
inertial, do you add the masses, then you multiply by r squared, or do you like put one mass and then add one mass and then multiply that mass by r squared?
And what do you mean, like, if you have like mr squared?
Yeah, but it has like the summation, so do you add the masses then multiply by r squared?
Yes. Sorry, like in what circumstance? Sorry.
Like quantity m1 plus m2 and then r squared.
Yeah, you can do that. Or if you have like, if you do like m1 r squared plus m2 r squared, you'll get the same thing.
Oh, okay.
And then if you do like m1 plus m2 r squared. Sorry. Does that make sense?
Yeah, we're just making sure.
Yeah.
I
Anything
do-
else?
I do have one with inertia.
Okay.
We do question 2.
A rod of length L and mass
Let me
M
take this off.
is attached at one end to a frictionless pivot and its initial translation acceleration of its right end. Interesting. Okay. Wow, your professor really like, okay, goes hard, I guess. That's good. Okay, so your moment of inertia. Do you have the formula for it, by any chance? Yeah, like that includes angular acceleration? Okay, yeah, sorry. All right. Let me just write it quick. I equals I squared, and then I of a. Sorry.
Parallel axis theorem is like
Yeah,
Parallel
parallel
axis.
axis theorem.
And
That
then-
is not something I remember doing in physics 1. Do you guys do parallel axis theorem? No, it's okay. We can still go over it.
wonderful.
I mean, you'll use it later, like in statics. If you don't have to take statics.
Yeah, it's not. They didn't make
Science
it
major.
Oh well, then I guess you won't.
Major.
I'm sorry, but yeah, parallel axis theorem. I think it's like I alpha equals. What is it like?
Parallel axis theorem.
MVD? No. Oh, okay, so it's like 1.
He told us it's just like. Since it's a thin rod, it's this one. It's 1/12 ml squared.
Right, it's 1/12 ml squared, and you're supposed to
It's the moment of
equivocate that.
inertia.
Yeah, that's the moment of inertia, which is supposed to be the same as.
Moment of inertia after one rotation, and somehow it's supposed to use acceleration to figure out the
Yeah,
velocity.
because you have to use acceleration. That's like the problem. I'm trying to remember it.
So,
This is really a lot. What? Do you guys have a different book too?
this is honors. I'm not sure if that's why it's
Oh,
different.
okay. That's probably why it's different. Yeah, some honors teachers really like push for the for their knowledge, which can be good. I mean, it might not be as useful for you if you're not taking like statics.
I mean, I don't even. All the formulas are usually at the end.
Okay.
So like, this would be pretty much all the summary of all the formulas from all supposed to do anything with like torque maybe?
I want to say
Maybe.
yes.
Wait, did you guys do gravitation? I said a gravitational force between two different objects.
Oh,
Like GM1, M2 squared.
we barely touched upon
Do
it.
not?
My God.
How about,
You guys covered a lot of content then.
how about, what if, 3 times a week?
Oh, 3?
Yeah. What about like, whatever chapter 12 is?
Whatever chapter 12 is. Yeah, chapter 12 is mostly center of mass and what's the other thing? Like inertia. Inertia and torque.
Okay. I mean, we can do anything, like, my only file is 10 through 12.
Okay, yeah, let's do this. So,
Well, I have 10 through 12, 13, and 15, but apparently nobody else has 13 and 15. We also did fluids, but we only did it for homework and not in class. So he just gave us an homework assignment, just said, all right.
serious net force.
We also had a quiz.
curve, right?
Like, what do you mean?
Like the regular curve that everyone has, the 10%. Like where you get an 85. To get an 85.
Yeah. Harry Potter.
Okay, so I need to. Do you have the formulas for that by any chance? I'm sorry, I wasn't really prepared for like harmonic. Like no one's really been asking. No, that's okay.
Cross them out.
Sorry, you crossed them out.
Would this be it for it?
If you guys aren't doing it, we shouldn't bother. Like, I'm mostly.
Well, you guys did some, I guess, right?
Yeah, we
Okay. All right. So. Yes, she has some for like the physical. Okay, so. So MA equals negative KX.
What is it? It's like the square root of I over mg hours equals a period.
Yeah.
Times 2 pi.
And then it's, if you're gonna solve one, it'd be the square root of 2L, or
The what?
yeah, L over mg, the square root of it. That one is when we solve it.
Oh, really?
Okay, so for this one, the question.